Hi, so we're just going to go a step further with this relationship I showed at the end of the last video and talk about, if we assume ideal gas behavior, what do we derive here? All right, so if we want volume is going to be equal to nRT over P, right? So if we want to find this for a molar Gibbs free energy, so that's often what we think about delta G bar, so molar, then n equals 1. And so we can then make a substitution here, go from P1 to P2 of RT over P dP. This is another straightforward integral. We've seen this many times. We get RT log P2 over P1. All right, and so this is a very useful relationship because it allows us to find the molar Gibbs energy, the change in molar Gibbs energy for a generic process here. Now, what we often do here, right? This is a change in Gibbs free energy. So what we'll usually do is define P1 to be equal to 1 bar and call that the standard pressure. And we use that as a reference point. So we can say that G bar at some temperature and pressure minus G naught at a temperature is equal to RT log P over 1 bar. Or we can rewrite this a little bit and say the the Gibbs energy is equal to, at some temperature and pressure, is equal to positive G naught T plus RT log P over 1 bar. Often we'll drop the 1 bar that's on the bottom here and say that, okay, P has to be in terms of a bar. Let's define this term here, though. This is G naught. So this is the standard molar Gibbs energy. You may know it doesn't have a bar over it because by definition, if you have the standard, it is a molar quantity. So we don't need the bar on the top. And the standard means that the substances are in their standard states. To be more specific, for the different phases they can be in, gases are an ideal gas at 1 bar, a liquid is a pure liquid under a pressure of 1 bar, a solid, same thing as the liquid, but it's a solid. And then solutions are a little bit odd. They're a 1 molar ideal solution. I'll put that in quotes. And we will explain what that means later. So this is not quite the same as standard temperature and pressure. There's no defined temperature here, so this is usually given at 298.15 Kelvin, but you can get standard molar Gibbs energies at different temperatures. But what this provides is a standard reference point that we can compare everything else to, because usually what we're interested in is a change in Gibbs energy, and so we need a point of reference for that. Similar to like we did for enthalpy, where we defined the enthalpies of formation for elements to be equal to 0. We're sort of defining a standard here too as well. And this gives us a standard reference point that everyone can use to compare different thermodynamic variables.